We'll now be looking at any exothermic change from a theoretical perspective to explain how energy flows from a system into the surroundings. According to the law of conservation of energy, the energy of any reactant system before and after a chemical change must remain the same. How do we explain a rise in temperature in some chemical changes? The answer to this has to do with an interchange in the potential and kinetic energy of the particles of the system. In exothermic chemical changes, the chemical potential energy of the products is less than that of the reactants. This difference in potential energy is manifested as heat energy, which is used to raise the average kinetic energy of the particles of the products. The system thus experiences a rise in temperature. For this reason, the container in which the reaction is taking place feels warm or hot. In a perfectly insulated system, that is called an isolated system, the energy produced by the reaction remains in the system with the product molecules having higher average kinetic energy. In a closed system, however, where energy can enter or leave, the heat energy produced eventually flows from the system into the surroundings. So we look at this figure here that shows the interchange of potential energy and kinetic energy between the reactants and products for this exothermic change. In this reactant system, the reactants, methane and oxygen, have high chemical potential energy but low kinetic energy. When they react, their molecules are rearranged to form carbon dioxide and water as products. These molecules have more stable bonds than those of the reactants. As such, some potential energy is changed to kinetic energy that is manifested as a rise in the temperature of the system. If the system is not well insulated and the temperature of the surroundings is less than that of the system, heat will flow into the surroundings until the system attains the same temperature as that of the surroundings. There is thus a net loss of energy by the system. A similar reaction to this is what happens when gasoline is burnt in combustion engines of motor vehicles. The heat produced is used to raise the kinetic energy of the carbon dioxide and water molecules produced to push the pistons up and down. Something similar to that happens in this reaction here that involves the reaction between magnesium and hydrochloric acid that give you magnesium chloride, hydrogen, and energy. Here we're having the system before reaction took place, which was at 22 degrees Celsius. After the reaction has taken place, the heat produced caused a rise in temperature of the system. Because the temperature of the system became higher than that of the environment, it lost heat until it attained the same temperature as that of the environment. These figures here show how methane is burnt in oxygen. Initially, the reactants are at 22 degrees Celsius, which is same as the surrounding temperature. We are having methane and the oxygen molecules there with their original kinetic and potential energies. However, after the reaction has taken place, the product molecules here, water and carbon dioxide, are having less potential energy but greater kinetic energy that is manifested as a rise in temperature. If the system remains isolated, that is, it does not allow any matter or energy to flow into and out of the system, the temperature within the system will remain at 90 degrees for eternity. However, if this system is changed to a closed one, that is, let us suppose we have removed this insulation here, heat will be lost by the system to the environment. This is the explanation of how during an exothermic reaction the system loses energy to the environment. We will now use an energy profile diagram to enhance our understanding of exothermic changes. This figure here represents the energy profile diagram for an exothermic change as exemplified by the reaction between gaseous hydrogen and chlorine. For a chemical reaction to take place, the molecules must have a minimum amount of energy that is called energy of activation. This is the amount of energy that allows the molecules to collide with each other in order to break their existing bonds and to allow their free atoms to recombine and form product molecules. The energy to do this is provided by the kinetic energy of the reactant molecules. Segment A to B represents the hydrogen and chlorine molecules approaching each other with their respective kinetic energies. Recall that the positive nucleus in any atom is infinitesimally small compared to the rest of the atom. The atom itself can be considered to be a comparatively huge negative electron cloud. So as reactant molecules approach each other, they inevitably experience forces of repulsion due to their negative electron clouds. It is similar to these two bark magnets approaching each other with their like poles facing each other. As these two magnets are brought progressively closer, the force of repulsion between them gets greater, and it is greatest at this point where the magnets are closest. At this point, the magnets have the greatest potential energy. If the magnets are released and allowed to move freely, they will return to their original positions. In that case, the potential energy is changed back into kinetic energy. A similar kind of thing happens with approaching molecules. The closer these molecules get, the greater is the force of repulsion between them until it is greatest at this point, when an activated complex is formed. This activated complex represents a species in which the old bonds are partially broken and new ones are partially formed. It has the highest potential energy, and it can do one of two things. It can reform to form the original reactants with their original kinetic energy, or it can go on to form products. So segment A to B represents the molecules approaching each other with their kinetic energy. Their kinetic energy is used to overcome their mutual repulsion. So segment B to C represents the molecules approaching each other with their kinetic energy that is gradually being changed to potential energy. This here is the activated complex that is formed. This line here represents the activation energy in the forward direction, and it is the amount of kinetic energy that the reactants must have to overcome their mutual repulsion with the eventual breaking of their bonds. So on this side of the curve, bond breaking takes place. There is gain in potential energy, but a loss in kinetic energy of the reactants. So let us see what happens if this activated complex goes on to form products. So that was our activated complex. These were the original molecules. We needed to break these bonds here such that this atom could have reacted with that atom there to form a new compound. So let us suppose that that's our activated complex here, and you have these two atoms here. Bond making is going to start to happen. How does that happen? Recall that a bond is formed when there is overlap of the atomic orbitals of the two reactant species. So here we are seeing that there is a greater degree of overlap, and as that happens, the bond strength increases in that direction. However, there is now a loss in potential energy, but a gain in kinetic energy. And this is manifested as heat that is used to speed up the molecules of the products. So if you look at this profile diagram here now, you can see that the atoms are getting closer and closer to each other. The bond is increasing in strength. So we see on this side is bond making. As the bonds get stronger and stronger, there's gaining kinetic energy that is manifested as heat that is used to speed up the molecules. According to this profile diagram here, the product molecules have greater bond strength than the reactant molecules. And as a result of that, the products will have less potential energy than the reactants. However, they'll have greater kinetic energy than the reactants. And because of that, the system experiences a rise in temperature. And the difference here is what is called the enthalpy change of the reaction. And you can see it is a negative sign here. That means it is an exothermic reaction. If you compare the bond energies of the products with that of the reactants, you can see here that the product molecules here have a total bond energy of 862 kilojoules, while the total bond energy of the reactants was 679 kilojoules. So the difference in bond energy will be that for 2 moles. So this is what it's going to be for 1 mole of HCl formed. And that is why you can see you have a rise in temperature, because these bonds here are more stable than those. This is the explanation for an exothermic reaction using the energy profile diagram.